Good evening. Shortly we'll hear an interesting lecture by Dr. Eyal Shekel on advanced laser welding with dynamic beam. This is part of webinar series organized by Photonics Israel on various aspects of photonics. Photonics Israel operates within Engineers Association as a cluster of photonics entities. Since we started operating last year, we have established close relationships with similar clusters in the US and Europe. Our mission is to deepen the knowledge in this area and to encourage cooperation both within Israel and with photonics entities in the world. We are open to your suggestions and would love to have foster new local and international collaboration. My name is Shlomo Glaser. I'm the manager of Photonics Israel. This webinar was prepared in collaboration with the Israeli Forum of Laser Material Processing. Dr. Eyal Shekel is the founder and CEO of Sivan Advanced Technology Limited, a Jerusalem-based high-tech company in the field of electro-optics. Since its established in 2008, Sivan focus has been a development of high-power lasers. Sivan products line include single-mode laser with CW power ranging from 10 watts to tens of kilowatts. The advantages of Sivan's laser include high reliability, high well plug efficiency, energy saving, low cost, and low maintenance. Dr. Shekel, the stage is yours.
Thank you very much. Thank you, Shlomo. So I will share my presentation. Okay. So I will start with just one slide, general information about Sivan. And then we will talk a little bit about the advantages of laser welding in general. A few words about the basics of lasers to explain how it has to do with welding. Then we'll talk about some advanced laser welding. And then we'll talk about Sivan's dynamic beam. So, as Shlomo said, Sivan was established at 2008. What we do is we manufacture high-power lasers based on coherent beam combining for material processing. We are 180 people. We're operating from 5 floors. We have a building in Jerusalem, 3,500 square meters. We have a proven track record with many customers. We've been selling products for the last 12 years. We are a vertically integrated company, which means that we have in-house production of all the core technologies. We have more than 50 patents, and we do a lot of collaboration with many different research groups in Israel and abroad. And we're based in Jerusalem. So, what is laser welding? When we compare laser welding to regular welding, so first starting about, what is a laser? A laser at the end of the day is just a source of light. But when you sit in a room like this, you have probably a few hundred watts of light in the room. But if you take a laser with a few hundred watts, you can actually cut metal. And the difference is that a regular light source, the light is scattered all around, whereas in a laser, all the light is focused and directed to one direction. And the result is that when you use a laser for welding, all the energy is focused and all the heat is concentrated, and you can get a very well-defined, narrow weld, compared, for example, for a tungsten arc, where the heat is spread over the weld and you get a much broader weld. So that results in a few advantages. So first of all, the fact that all the energy is focused means that you have a very small heat-affected zone. You can get a much deeper penetration. The overall part has much smaller distortion. You can get to higher, to faster welding speeds, and you are much more efficient using your energy. All this is because the energy is focused to a very small area, and then basically the time that it takes the heat to move away from from the weld spot, you get the welding process running before the heat spreads out. You can also control the keyhole shape. You can control the keyhole shape by basically controlling the power, the feed speed, the focus of the beam, and so on. And you can have different shapes of the keyhole. And this way, you can control, optimize the keyhole for the different welds that you want to do of different materials. If you want to do dissimilar materials, and adjust every parameter for the material that you want to weld. Another advantage is the ability to do welding without a wire. So if you compare here to a TIG welding where you have the filler wire, in a laser welding, you can do the welding without the filler wire. So that gives you a much more flexible process because you don't have to make sure that the wire gets to the right place and you don't have to feed the wire. So you can do remote operation. The process can be easily automated. You can do welding of very thin materials where there's no room to add a wire, and there's no post-processing needed after the weld. So what is the basic concept of a laser? One of the most important concepts of a laser is the beam quality. As we just described, one of the big advantages of the laser is because you focus the beam to a very small spot. But the ability to focus the beam to a small spot has to do with the beam quality. So what we see here is a Gaussian beam, what's called a single mode laser with a Gaussian beam. This is the optimal beam shape, which allows you to have a very good focusing capabilities, compared to a multi-mode beam, which has lesser properties. Usually, when you go to high power laser, the beam quality is degraded because you have to take a lot of power and concentrate it to one place. And we'll talk about it in a few slides. But basically, the difference between a single mode beam and a multi-mode beam has two effects. First of all, with a single mode beam, you can get a much smaller spot. So if you start with the same aperture with a multi-mode beam, which is the red here, compared to a single mode beam, you can see that the single mode beam can be just much smaller spot size. The other thing is that the depth of focus is much bigger in a single mode. So what you see here is a single mode beam that starts from a smaller aperture, gets to a very small spot, and this small spot is maintained over a large depth of focus. Whereas in a multi-mode beam, in order to get to a small spot, you have to use big optics, focus the beam very sharply, but then your depth of focus is very small, meaning that when you move a little bit out of focus, the beam size becomes very big. So with single mode, the advantage is that you can work from far away, you have a very deep depth of focus, and you have a very small beam, even when you work from far away. So that means that you can have the laser here, have some fiber coming to a mirror, and the mirror scans and jumps from place to place, and you can do remote operation. Now, this remote operation has another advantage, and that is the speed. What we see here is a multi-mode laser cutting thin sheet metal. In order to do that, I'm going to go back a little bit. In order to do that, because the depth of focus is small, you have to work relatively close to the workpiece. And then the whole laser, the whole optical head, has to move in order to make the cut. Whereas in single mode, you can work from far, like we showed in the previous slide with a mirror. The mirror can move very, very fast, and you can see here remote cutting at 50 times the speed of the equivalent multi-mode cutting. This is a courtesy of Fraunhofer IWS. This is done with a single mode laser. So we discussed until now just general laser welding, but with a laser, you can do advanced welding by adding some additional features to the laser. What we see here is an example of welding of aluminum tube to a die-cast metal. And when you just try to weld them, you get a very poor quality weld. And the reason is because the aluminum and the die-cast have completely different properties, both in terms of heat conductance, heat capacity, melting temperature, and so on. So if you would just come with a heat source and try to weld these two dissimilar materials, you get a poor quality weld. But if you have a laser beam, a small narrow laser beam, and you move it around, you can move it around inside the melt pool in order to control the energy distribution and the heat gradient and heat distribution in order to get a very good weld between these two materials. This again is work done by Fraunhofer IWS. Another similar example is when you want to weld in overlap welding, when you want to weld copper to aluminum. If you just come with a single heat source or a laser beam, just a standard stationary laser beam, you get mixing of the materials and you get a very poor quality weld. But if you move the beam around by oscillating the beam, you can control the width and the depth of the weld. You can control the lifetime of the melt pool and the gradient, the temperature gradient of this melt pool, making sure that you don't have any mixing and no intermetallic phases, and just in general a very, very good weld. Another example is we see here welding of copper, and what you see here is a lot of sputter. And this sputter occurs because you have basically a lot of power going into material and you have these explosions. But if you can modulate the power, you can actually have a sputter-free weld. Okay, so this is done by modulating the power and making sure that reducing the power before you create sputter. This is the work done by University of Stuttgart, IFSW. So what we see is that when you want to go to advanced methods of welding, you need a much better control of the beam. It's not enough just to take a lot of power and concentrate it in a small spot, but you actually want to control the melt pool. And many companies are working on doing some beam shaping or beam steering. And what we can see here is, for example, Enlight has the Corona laser that has different shapes for the beam. You can see a small spot, larger spot, donut shape, or different types of donuts, or even combining beam in the center, energy in the center with the donut. And you see the same thing for IPG, what they call the AMB, and the coherent arms, where you can have a spot, a donut, or a combination of the two. Amada also came out with the Ventis system, where there is beam steering. Basically, they take a small beam and move it around to create this beam steering, again, for controlling the melt pool. And IPG also has this beam steering to control the melt pool. The results are very nice. This is example from Coherent. This is again just from their publications, just to show the importance of the beam shaping. So this is an example where they use a donut with intensity in the middle, and this is welding of aluminum, and you can see a very good weld, no cracks, very uniform penetration along the weld, and no porosity at all in this weld. And this is achieved by a sophisticated beam shape, not just taking a Gaussian beam or a top head, but rather a more sophisticated shape. And this is an example from Enlight. Again, you see where we have a sophisticated beam shape. So this is a standard Gaussian beam compared to the Corona fiber laser with different beam shapes. And you can see in these graphs that you can do deeper penetration and much smoother. You can see here the roughness, much smoother cross section. So what we saw till now is, first of all, the advantages of laser compared to the standard welding, where a laser can focus the energy to a very small spot, and therefore having all the heat concentrated, so we have a much cleaner, smaller heat zone, and so on. And then we showed the more sophisticated beam shapes that allow for a higher quality weld. And what I want to show you now is Sivan's dynamic beam, which is really the most sophisticated way of doing beam shaping and beam steering. And the Sivan coherent beam Sivan dynamic beam is based on coherent beam combining. So what is coherent beam combining? Just in a few short slides. The idea of coherent beam combining is that we can take many lasers and combine them together to work in one single mode output. As I mentioned in the beginning, you can have a high power laser, so you can have a laser with a single mode output, but when you go to high power, usually the beam quality is degraded. The unique thing about coherent beam combining is the ability to get to extreme high power and still maintain the very high quality beam, plus, as I will show in a minute, the ability to control the beam shape. So what we see here is a very schematic way where we have a seed laser, we amplify it, we control the relative phases, amplify in many amplifiers, and combine them to have a single mode output at tens of kilowatts. And there are two methods to do coherent beam combining. One is what's called field aperture with a single mode output, where we take several lasers. In our case, we can take tens of lasers, each laser with a kilowatt output, to a common optical element. And by controlling the relative phases, we can have the energy of all these lasers coming out as a single mode output, having here tens of kilowatts with single mode output. The other method is called optical phased array, OPA. And the idea is that not only you can get a single mode output, but you can actually control the position and shape of the combined beam. And here we can actually get more than 100 kilowatt with a single mode output and a dynamic beam. So how does that work? So every laser, when you turn it on, will have some kind of a cone of light coming out from the laser, creating some spot of light. And when we turn each laser individually, each laser will have this cone of light creating a spot. But when we turn all the laser on together, there is actually overlap between the lasers. And in the overlap zone, there is destructive and constructive interference between the lasers. And in places where there was light before, okay, so if I go back here, so in this whole cone of light, there was light. You actually get destructive interference and you get areas of darkness or very low intensity light because there is destructive interference between the different lasers. And all the energy from all these lasers is concentrated in this area. So what we get is these lasers, and when they overlap, you get this interference pattern. And by controlling the relative phases between the lasers, we can actually control the output beam to change position, change shape, change focal distance, and so on. So we actually have full control of the output beam shape, position, and focus just by changing the relative phases. Now, changing the relative phases is something that's done in electronics, which means that you can do it at gigahertz with no moving parts and have an arbitrary shape with no mechanics involved. So everything that we discussed before about advanced material processing, advanced welding with using sophisticated shapes, we can do any arbitrary shape at gigahertz speeds with no moving parts. This is what a laser looks like. So you can see here with the doors open that there are tens of amplifiers. Each amplifier has a kilowatt. So if you look at the schematic, the idea is that we combine tens of lasers, each one with a kilowatt, to a common output. So here you see these individual lasers, all combined through this fiber to an optical head, and the common output comes out from this window with tens of kilowatts, single mode with dynamic beam. Currently we have 20 kilowatts, and we are shipping out now a laser with more than 100 kilowatts of combined output single mode beam with the dynamic options. So our dynamic beam can do any arbitrary beam shape. We can do beam steering. So we can basically move the beam around, and you can move the beam either at gigahertz speed, which effectively is like having some kind of a beam shape, or we can do it at kilohertz, which is really steering the beam inside the melt pool. So for example, over here, you can see you can do any arbitrary shape. For example, for welding two dissimilar materials, you can deposit a different amount of energy in one material than in the other material. We can change the focus, so you can focus the beam in the depth of the material. We can do power modulation, like we showed before, controlling the melt pool to have a sputter-free weld. And also interesting, if we try to drill through some composite material with several layers, we can drill and change the beam parameters as we go through. So for example, if it takes 400 nanoseconds to drill one layer and another 100 nanoseconds to drill the second layer and another 500 nanoseconds to drill the third layer, each layer will have its own beam shape and beam parameters as we drill through to have a perfect drill. Each material gets its tailored beam. So here we see some examples of arbitrary beam shapes. This is all done at 14 kilowatts, and you can see just any arbitrary beam shape. You just jump from one beam shape to a different beam shape, and again, this can be done at nanoseconds between beam shapes. We have a very simple software that allows the user to design any arbitrary beam shape that they want. So basically, you have this chart where you mark any shape that you want. You can choose the order by which the beam is going to go from area to area. And you get right away a simulation of what the beam is going to look like. So you can see here that the shape was not perfect. Okay, in the simulation, you get a shape that is not exactly what we wanted. So we can go back and do a little bit optimization to the beam shape, move things around a little bit, change the intensity in every area, and get a simulation of what the beam is really look like. And then all you have to do is upload this file into the laser, and then you can just pull it from the laser anytime and you get this beam shape. So what you see here is the design, the simulation, and then the output. This is at full power, 14 kilowatts, and you can see that the actual output is very similar to the simulation. Okay, so you see here, this is at 14 kilowatts, very similar to the simulation that we showed in the software. So this all gives us the ability to control the melt pool by controlling the beam shape and beam position. We can control the depth of the focal point. And basically, by doing this all together, we can control the position and shape to get a full control of the melt pool. Now, when you compare it to what we showed before about what other companies do, so so like we showed Amada or IPG that can do kilohertz beam steering. By us, it can be done at megahertz. Usually, when you have a mechanical scanner, you have to go at some symmetrical shapes or at least continuous shapes. With Sivan, you can do any arbitrary shape. It's not a mechanical motion, so you can do it much faster, no moving parts. You can get to much higher power and do it much faster than any other method available in the market today. So to summarize these advantages, we're talking about the ability to do keyhole modulation for spatter-free welding. We can do a melt pool modulation to get a homogeneous mixture. We can do a temperature modulation to reduce the transient stresses, and keyhole modulation for non-humping high-speed welding. The point is that every process, every type of weld is going to need its own beam shape. It's different if you do cutting or welding. It's different if you do thick material or thin material. Every material will need a different optimization. If it's crack-sensitive materials, it will need different shapes. So every process is going to need its own specific beam shape. But as you saw, it only takes minutes to design any beam shape, and you can optimize the beam shape, and it takes minutes afterwards to upload any beam shape into the laser and actually optimize to get the optimal process. In the future, we think that we also be able to do real-time adaptation, because we can change the beam shape, like I mentioned, in nanoseconds. So if you have some high-speed camera or pyrometer or OCT, you can actually, during the process, optimize the beam shape to get the best possible process. So in Sivan today, we have our application lab. We can see here a 16 kilowatt laser with the optical head going to an XYZ table. And you can see here the control room where we control the laser. So you can see here, we can see the beam shape coming up. And we see here the workpiece as it goes through. And this is where we do all the experiments and process development for different customers. We also have a small metallurgical lab where we can actually take the samples and analyze them. And this is just a few examples of what can be done. And you can see with different beam shapes, of course, you get completely different cross sections. And this is the ability really to design any beam shape, use our application lab, and do process development for any process that's required. So today we have 3 product lines. Most of my talk was about this product line right here. This is the OPA CBC single mode laser with dynamic beam, where we have different power levels up to 21 kilowatts. And soon, like I mentioned, we can have up to 100 kilowatt output. We also have the single mode laser, if you just want a static single mode beam, up to 10 kilowatts. And we also have a green laser, which has its own advantages in welding. So thank you very much, and I'm open to questions.
Right, and now the session is open for the questions of the audience, please. There is one question on the Q&A. Can you see it, Eyal?
Yes. Okay, so the question is, can this method be generalized to ultra-fast picosecond lasers? The answer is yes. We demonstrated pulsed operation with a coherent beam combining, but it's not something that we did a lot of work in. We are currently focusing on the very high power CW lasers, but in general, it is possible to do it also in pulsed mode. The other question is, what is the main industrial use of your lasers? So really, we are now working in cutting, welding, and drilling. This is in the high power. And we also have work in additive manufacturing, metal additive manufacturing. First of all, in additive manufacturing, the control of the melt pool is also very important. But in addition, this is something I didn't discuss in this presentation, but our ability to do beam steering in any arbitrary way and very, very fast also helps to do 3D printing much, much faster, basically complement the mechanical motion of the beam with the electro-optical motion, and together possibly get 20x factor in speeding up the additive manufacturing. So just to summarize, cutting, welding, drilling, and additive manufacturing, these are the areas that we are operating today. There's another question here. Are there any safety issues with the electronic control? Of course, this is an extreme high power laser. There are many safety issues. Our laser is fully equipped with all the safety features, interlocks of any kind you can imagine, but of course it has to be worked within an enclosure, just like any other high power laser. What is the price of the machine? So this is a question that you can contact us because there's no one answer, there's a whole range. We have lasers going from tens of watts up to 100 kilowatt. So, you know, we'll be very happy to discuss the application and give you the price quotation for the right machine.
Yeah, you shall call Sivan and they will provide you the price. There is a question on the chat. Can you read the chat?
I don't see a chat. I see the Q&A. Oh, I see the chat, just a second.
What are the advantages of different wavelengths?
Oh, okay, great question. So basically, fiber lasers, as well as the YAG laser and disc laser, are all working in 1 micron. Now, I don't have this chart here to show, but it's very well known that many materials have very high reflectivity in the 1 micron. So aluminum, copper, silver, and gold all have very high reflectance in the 1 micron. When you compare it to a shorter wavelength like green, 530 nanometers, 530 nanometers has much lower reflectance, which means much higher absorption in 530 nanometers. So the ability to have a green laser, or you also heard about blue lasers, but Sivan has green laser, which is extremely important for these materials, aluminum, copper, gold, and silver, for doing much more efficient, much cleaner welding of these materials. And we have, as far as we know, the highest power single mode green laser. And this again is done because we do coherent beam combining of green lasers. So we have today 150 watt single mode green laser, and we're working now on 500 watt and possibly a kilowatt of single mode CW green laser.
Eyal, the second part of this question of David, does your technology have advantage in removing surface layer, e.g. rust removal?
Yes, so yes, thank you for the question. I didn't mention this application, but basically surface treatment is also something that we can do because the very fast beam steering. When you have to do a surface treatment, basically you have to cover many square meters very fast with very small resolution. So basically you have a spot size that is tens or hundreds or microns, and you have to cover many square meters. So you have to move around very fast. Today, usually it's done with a pulsed laser. The problem with a pulsed, so you have a pulsed laser with a scanner. The problem with the pulsed laser is that it has a duty cycle, which means that a significant part of the time the laser is actually off. Our laser is high power, high brightness, moves very fast. So in combination, the electro-optical beam steering together with the mechanical beam steering and the very high brightness allows you to do surface modifications very fast and much more efficient than when you do it with pulsed laser.
Okay, you have more questions on the Q&A?
Yes. So is it possible to use subtractive ultra accurate manufacturing? Again, the answer is yes. Like I just described, and we do drilling, and we can do just subtractive manufacturing. Like I mentioned, again, comparing to a pulsed laser, we can again reach the extremely high brightness, very high concentrated energy, and move very fast. The question is, do you have already machines in the market? So the answer is yes. We have machines in the market by several customers. I have to say it's really in beta sites. It's not in mass production, but we have several beta sites with customers, and everybody is invited to come to our application lab and see the lasers working. Send us your samples, and we can do process development for your specific needs. Yes. Okay, there's a question here is, how do you control cooling cracks at the heat deposit is low, so the cooling speed is high? Okay, so I guess the question is, if you have a crack sensitive material, basically, when you come with a very intense heat source, you create a very big gradient in temperature, which creates the cracks. And this happens sometimes in the heating and sometimes in the cooling. But bottom line is that when you come with a very condensed heat source and you work very fast, you create cracks. Now, what we can do with our beam, when we demonstrated that it can be done, you actually divide the energy between different areas. And basically, if you take the beam and you divide it to different areas, so when you move the beam along the weld, you start with an area that basically just heats up the material. And only then you go to a highly concentrated energy section where you do the actual melting of the material. And then you can have a trailing edge that keeps the lifetime of the melt pool longer and creates a lower gradient in the cooling. Okay, so again, to say, you start with some leading edge, you have high energy in the middle, and then you have a trailing edge, and this reduces the gradient by which you heat up or cool off. And of course, every process has to be optimized. Also by doing beam steering, you can optimize this, but with the right simulation and with the right design, you can develop the process to avoid these cracks.
Yeah, for a moment, I would like to ask Dan Har-Even, Eli Ben-Aryeh, Ephraim Gurfinkel, and Gidi Datan, please rewrite your question on the Q&A so Eyal can read it directly. Okay.
Do you need an inert environment for welding? So this really depends on the process. Just like any other weld, sometimes you need the inert gas, and sometimes it's not necessary. I can say though that with the dynamic beam, because you have a very, very small high intensity beam, sometimes you can overcome the need for inert gas, but it's not a general answer. Okay, so it really depends on the process, but we believe that at least in some occasions we can eliminate the need in the cover gas. There's a question, did you have a chance to test green laser on organic substrate? The answer is no, we did not do this test yet, but we'll be happy to try if you have some specific tests you want us to do. Can this presentation be sent to us? The answer is yes. This presentation can be sent. It's nothing confidential here. How much do you rely on non-Israeli technologies? We buy components from all over the world, but I don't think there's any technology that cannot be done in Israel. I see Chaim is asking the question, Chaim Russo, and I think this is, I mean, what we do today, for example, that is not made in Israel yet are two things. It's the diodes and the fibers themselves. Both are now, we have the Israeli center, the photonic center that is now operating, and hopefully very soon we'll be able to also have diodes and fibers that are made in Israel. These are the only two components that are not made in Israel today. What is the laser efficiency? So the laser efficiency is roughly 25%. Basically, the fiber laser itself has about 30–35% efficiency, and then there's some reduction in efficiency due to the coherent beam combining, but the overall laser is roughly 25% efficiency. And did you try glass substrate? Again, the answer is no. We didn't get to try glass substrates yet. But again, if somebody has a specific need, we'll be very happy to try to develop a process in our application lab.
Okay. Dr. Shekel, thank you very much. Very interesting lecture. And I believe that you will get some mail in the future.
Looking forward.
Right? So thanks.
Thank you very much.